Good morning, class. Can you hear me?
Good morning, Doctor. Yes.
Okay, so we will record this session. Okay, and I couldn't remember whether it's requested from your class or the other class. They have preferred to work on the tutorial session, okay, as what we have done last week. So therefore, instead of the lecture, I'm talking by myself. We are going to do directly solving an example for the frame. So the PDF, the compiled examples that I have shown you, you can read it, okay, by yourself. Okay, of course, I'm preparing right now for a video on the frame example. I hope it can be ready by tomorrow, okay, and to be posted to YouTube. I will share you the link, okay, if I can do it by this week. Okay, so but there is one pre-recorded video on trust analysis that is solely on the lecture. I will share to you also. Yeah, the link is ready. Okay, I'm thinking either by today or tomorrow after your class. Okay, so now today we are going to work on an example for a frame. Okay, so we have gone through on how to prepare for the stiffness equations. Okay, so we are going to do that. There is a slightly modification, okay, if you compare to the beam example. Okay, let's see, okay, how we are going to go through this. Okay, but please get ready with your stationery, your calculator, your exercise book. Okay, take down this problem. I'm still writing it, so maybe you can do it together with me. Okay, this problem. Can you see my slides?
Can, Doctor?
Yes.
Yes.
Yeah, you can take down the problem, and we are going to work on this. Okay. So I need to put this in a greater form. Maybe not enough. How about 20? Okay. So let me check whether it's correct. This 50 kilonewton per meter, working on 6 meter span and the 6 meter the other spans. The height is 4.5 meter. Not that right. And DOF, I shall get this. Here, okay, A, move to here, and then this is this is 1, 2, 3. I want the DOF. Please, I'm so sorry. I want to move this DOF to 4, 5, 6, 7, 8, 9. Okay. So yeah. Okay, you can take down this problem first. Okay, can you see this? If not, I enlarge it again. Are you able to see the frame details?
Yes.
Okay.
Yes,
Can,
doctor.
Doctor.
Okay. So please take down. Once you have done, just let me know. We are going to start. Okay. Okay. Have you done? Take down the problem.
Yes.
Yes.
Before that, let me check whether we have all the participants here, all the students join. Yeah, all the students join. Do let me know if you cannot see the screen. Anyone? You may raise your hand if you have a mic problem. Let me see whether all can participate. All right. It seems like everyone can participate. If you have any problem, quickly let me know in the WhatsApp group. You cannot follow this tutorial. I will share, the progress of our the solution. The phase by phase. Okay. So now we are going to start with this. Okay. Okay, once you have get this problem, if you can see, let me read the problem. This is a frame ABC, which pin supported at A, and oops, sorry, can you help me to change this? Fixed. Fixed supported at both A and C, okay, and given the E value, I value, and the A value here, we want to solve the unconstrained degree of freedoms and the support reactions, meaning that we want to solve for the unknown displacement and also the support reactions here. Okay, so what we can do for this problem, we need to assign the nodes and the elements to the frame. Okay, as you know that we are going to divide this the whole system into finite elements. Okay, but because of our limitation in the manual calculation, we put the minimum, okay, minimum number of elements. Okay, so what you can do here, you can put the nodes, okay, at your supports. Okay, node number 1. Okay, I have already put it here, node number 3. Okay, and you can also put the nodes, okay, at whenever they have a different alignment. Like for example, if you can see the A, B, C, there is one span and they change the alignment. Okay, so at this particular joints here, you put node number 2. And if there is any change in terms of EI, EA, okay, you also need to put the notes, okay, to indicate the difference. Okay, so I see this node 1, 2, 3 is appropriate for this frame. Then we can put in the element. Okay, so in between the nodes, we are going to have the elements. So I will put the element number 1 here, okay, to indicate the this BC element 1, and B to A is element number 2. Can you follow class?
Yes,
Okay.
doctor.
Okay. So now the next thing is we want to draw an arrow, okay, to indicate the near end and also the far end. Okay, so at every element you need to have one arrow. Okay, so this arrow can be up to your, your preference. Okay, but if you are talking about a programming, they will follow, a specific rule. Okay, created by the programmer. Okay, so in this case, so we are going to put the arrow for element 1. Okay, so it must be aligned. Okay, same alignment with this element 1 along it. And then another one is for my element number 2. So now you will know that for element number 1, node 1 is near end, node 2 is far end. And for element number 2, near end is node 2, far end is node 3. Okay? So can I move to the DOF numbering?
Yes.
Okay. So now, if you can see that we are actually doing for frame. Okay. So if you still remember for beam, they are. If I said this is number of DOF. Okay. So the number DOF for beam at each node per node is 2. Okay. For truss is 2, and for frame is 3. Okay, we are talking about 2D system now. Okay, so the direction, okay, it can be shown by arrow. For example, for beam, it will be this direction, okay, corresponding to the shear and the moments. And for truss, we're talking about the X and Y direction. Okay, so this can be talking about Y direction. This is Z direction. This is X and Y direction. And for frame, okay, it will cover all the X, Y, and Z direction. Therefore, you need to put this indication for all the nodes. Okay, so if you place at all the nodes, there are 3 nodes, so the total DOF for this system is 9. Okay, so you can imagine you shall have 9 times 9 matrix, okay, in your stiffness equation later. Okay, so now after you have put in all these the DOF at each of the nodes, we need to give a number. Okay, labeling, numbering. Okay, so this numbering or this coding, okay, sometimes they put in the reference book. So are called with rules. Okay, if you still remember, the rule is we label or we give a number to unknown DOF first. Then only the known DOF. So DOF here means the displacement permitted for that particular node. In this frame, it can move X direction, Y direction, and also Z direction. So now for us to be able to number this DOF, it will be my advice to you is to identify where is the known value first for the displacement. So the known value of the displacement is always associated with your support reaction. So if you go to the support, see this frame, you will see that at C, for fixed support, the support reactions you can find is CX, CY, and also the MC. Okay, so meaning that at this particular direction, the displacement is 0. Okay, it cannot be moved. It is not allowed to move at that directions. Okay, so meaning that the displacement at C at horizontal is equal to 0. And for vertical, C is also 0. And then rotation at C is also 0 for fixed support. Okay, similarly at node number 3 or at A, These directions of the, displacement are also equal to 0. So meaning that the rotation at A, 0, displacement horizontal, vertical are all equal to 0. Meaning that these displacements are all non-value. So what we can do here, we already identify the non-value. So we name them later, not first. Okay, so the left DOF here, 1, 2, 3 at node number 2, they were named first. Okay, this is why the numbering is according like this. Okay, of course you can say that 7, 8, 9 can I name as 4, 5, 6? Sure, you can do that. Okay, so as long as you differentiate, because we want to partition which one is the unknown and which one is the known. Okay, it will be better for us to arrange or sort out, okay, our matrix. Do you have any question up to now?
No, doctor.
No, doctor.
Okay, so the next thing is we are doing for vector of D and vector of Q. Okay, maybe you can try first while I prepare for the write out. Okay, and the vector will be having a size of 9. There will be 9 times 1, 9 times 1 vector. Okay. Where's my slide? No, need to design myself. Just okay, are you ready? Can we try?
Yes.
Okay, so I'm sorry I cannot put a full screen because I want to edit the things. So now we know that I have write some statement here, but you no need to write in your solution. Okay, just for you to know. D1 to D3 are unknown displacement. Okay. And D4 to D9 is equal to 0. Correct or not? Just now we have had,
Yes.
yes. Okay, so we don't have any support settlement, okay, because I modified from an example with the support settlement. If you have a support settlement, you will have a value at the specific locations. So in this case, your vector, your displacement vector shall look like this. Okay, where D1, D2, D3 are unknowns, displacement, and the later is O0, the D4 to D9. Okay, do you get this answer?
Yes, doctor.
Okay, so next we are going to do the Q vector or force vector. Okay, so for this force vector, you need to know that Q is referring to support reaction or nodal force. When you have an external load, they apply at the nodes. And if you look at this problem, you don't have any. Okay, and you have a support reaction at number 4, number 5, number 6, which is at C, and also 7, 8, 9, which is at A. Okay, so therefore, Q4 to Q9 are all support reactions. Okay, do you get this also?
Yes.
Okay, so now you can do a partition to double confirm, double check, okay, whether your arrangements are correct. Okay, so you can do this. Okay, so therefore next time you just put your D vector and Q vector, okay, side by side, okay, just for you to double confirm. Okay, you can draw these partitions, okay, to check. Okay, so the one that you want to check is these are the Q unknown, okay, and these are the Q known value. You also need to check at displacement. This is the sorry, okay, so you need to check on this partition whether your arrangement is correct or not here. Okay, so now you will see that, okay, at this Q, for this partition line, you can partition, differentiate the known value of Q and unknown value of Q. Similarly for the displacement. Okay, so you will also you also can check that the known value of the displacement always opposite, okay, direction with the Q known, and the unknown of Q opposite with the unknown of D by this partition. So if you think, I mean, everything is clear for your case, okay, then you can continue. Okay, so next we are going to continue with putting the member stiffness matrix and structure stiffness matrix. Okay, so let me arrange this. Please get ready with your appendix right now. You shall referring to your appendix to get this template. Okay, so if you look at your appendix, there is K prime, T, and the K matrix. Okay, so you shall use this member global stiffness matrix, the K, to form your global stiffness equations. Okay, don't get wrong. Okay, so you must use this template. Okay, if you look at this template, there are, oops, animation. There are a few highlighted elements. For example, AE over L, 12 EI over L cubed, okay, lambda X, lambda Y, okay, 6 EI over L squared, 4 EI over L, 2 EI over L, lambda Y squared, lambda X squared, okay. So these are the elements that we want to determine first before we putting into the this template, okay. So it may take some time, okay, but the process is uh, very straightforward, okay. No need to think, just substitute the value, okay. So we are going to prepare for this. Before that, okay, because you haven't go through the my video on the how to get the lambda, okay, maybe you need to, I will explain to you what is lambda. If you look at your appendix, the lambda has been given in a symbol of C. So they are actually basically the same. Okay, so what is lambda or C here? Okay, you can give a name here. Wow. Okay, wait now. Okay, so this lambda actually the name is directional cosines. Okay, so this directional cosine, they are actually we are gathering the elements here to become a vector. Okay, based on the angles between this so-called vector with the coordinate axis. What is the vector? The vector is this one. Okay, let's say you have an element K. Okay, let's say you have one element. Okay, element 1 or 2 or 3 or so on. So I name it element K. Okay, so this arrow will show where is the near end. Okay, which indicate as I, and where is the far end, which indicates as J. Okay, so they are coordinate, okay, at these near end and far end nodes. Okay, then you are going to get actually the cos theta, okay, if you are for to determine the lambda x. Okay, wait, I have, so, hello? Yes, yes, I have. Oh, I'm so sorry. I forgot to close my video as well. Tergendala. So let's continue with this. Okay. Dekat mana? So here, this directional cosine, we need to determine actually the cos, okay, of this angle. Okay. If you want to determine the delta lambda x, we are actually referring to this element. Okay, the angle towards this x coordinate axis. Okay, if you want to determine the lambda y, okay, so we are actually referring to cos of this angle, angle theta y, which is referring to the y coordinate axis. Okay, so therefore you need to define where is the angle so that you can get, the cos theta correctly. Okay, but I will also like to share with you another method, okay, which is using the coordination, okay, which I myself prefer more. Okay, what you can do is, okay, for this element k, let's say, you write down the coordinate of the near end and coordinate at the far end. Okay, to get the lambda x. Okay, so this is nothing about the theta x and theta y anymore. We are just using the coordination, okay, coordinates at the near end and far end to determine the lambda x. For lambda x, you use the coordinate x. For the far end, minus the coordinate at the near end. For example, this, the x coordinate at the far end minus x coordinate at the near end, xj minus xi, and then divide by the length of the element. Then you get lambda x. The result must be the same with cos theta x. Okay, and for, oops, this is lambda 1. Okay, for lambda y, we will use the y. Okay, y coordinate at j minus the y coordinate at I divided by the length. Okay, so maybe we can try this for our element 1 and 2. Okay, so now what you can do is, give a coordinate to this your structure first. Okay, so can you help me? If we put a reference 0, 0 at C, what is the coordinate at B? And what is the coordinate at A? Class?
6, 4.5.
Okay, so this would be 6 and 4.5. And this one?
12.4.5.
Yeah, thank you very much. So now from here we can get our lambda x and also lambda y. Okay, so I'll put the lambda x here. Okay, for now we are doing for element number 1 first. Okay, element number 1. So the x value will be 6 minus 0. With the length, you need to calculate the length for me. Okay, so this will be 6. What is the length of the element 1?
7.5.
All right, correct. 7.5. So what is your lambda x now?
0.8.
Yes. So now we can also get the lambda y straightforward here. Okay, lambda y will be y at the far end minus y at the near end divided by the length. Okay, the length will be the same. So let us have a look what is the y. Y at the far end is 4.5. Y at the near end is 0. Okay, so we can put in 4.5 minus divide by 7.5. Okay, what is this?
0.6.
Thank you. Okay, so now you have get your lambda x and lambda y ready here. Okay, so what you can help me to do now, okay, to put in, don't get confused, I'm taking this from my other example. We are going to fix it now. The length is 7.5 meter, the rigidity is EI, and given the E is 200 gigapascal. The I is 225, and the A is 7,500. Okay, so from the following, you need to determine the AE over L, 12 EI over L cubed, 6 EI over L squared, 4 EI over L, 2 EI over L for me. Okay, substituting the area, the Young modulus, and also this I inertial. Okay, so can you help me to do that one by one? Okay, so let me open it. Okay, we have get this done. Okay, area is 7,500. Everything shall be changed to meter, kilonewton and meter. So this will be minus -6. Then we multiply with E is 200. Okay, gigapascal. Okay, and the length is 7.5. So yeah, please have some time to do this. Okay, I will collect this from you later. Okay, do you have any value for this? Maybe we call helps from friends. Okay. Nurin? Nurin Akila, can you help? What is the value for AE over L?
200.
Power? Any power?
Power 3.
Power 3. Thank you. So maybe we call another names here. Oh, there are two Nurin here. Fazana, Nurin Fazana. 12 EI over L cube.
I got 1,208.
Okay, how about maybe you can help the rest?
I'm still calculating, Doctor.
Okay. So let me ask. Yes, I heard 4,800. 800. Thank you. How about 4 EI?
24,000.
24,000.
Power
24 power of 3
of 3
plus
and
power 3.
12 power 3. Okay, thank you very much. Okay, so yeah, this is quite boring, I would say, but it is very straightforward. Okay, you just put it in, plug it in, and make sure you, the unit has been changed properly. Okay, to kilonewton and meter. Okay, if you cannot remember these units, I think you can remain only the value. There is no problem. Okay. So then what you can do here, please get ready with this template. Okay, I might not be able to show you all the time. Okay, we are going to place it into this template. Like for example, you get the AE over L lambda x squared plus 12 EI over L cubed lambda y squared. Okay, we are going to do that one by one. Okay, so what you can do here is this. Okay, this template, this is not the answer yet. I haven't put in the answer. How shall we do that? We need to get the information of this. Class, do you know what you need to do? Let me ask. Nurul Azira, do you know what you need to do now?
No.
In the matrices.
Yes, yes. So now you have already determined all these AE, 12EI, 6EI, 4EI, 2EI mana. And these are lambda X and lambda Y, right? So you need to put this, arrange this into this as the template here. For example, for this K11, for this one, for this, this is not the answer yet. Okay, we are going to determine for this K11, this value, means that you need to get from AE over L, which is 200 power 3. Okay, multiply lambda X squared, which is, oops, I haven't put it, our lambda X is 0.8. Okay, but 0.0, correct, 0.8 squared. And then plus 12EI over L cubed, you get it from 1280, multiply lambda Y squared will be 0.6 squared. Then you will get the value for this K11. And then you continue with all this value. Okay? Yang siapa tadi? Azira, now, are you better?
Yes, doctor.
Okay, so now let's start one by one. Okay, so let me fix this lambda X first. Okay, lambda X 0.8, lambda Y is 0.6. Okay, you can also, if you want to get the lambda X squared, lambda X, get ready with this, you can do so. Lambda X squared 0.8 squared, which is 0.4, and lambda Y squared is 0.36, lambda X be 0.48. For whom cannot understand what we are going, please to interrupt here. Okay. So maybe let us call names, okay, to help us here. I think before that I shall increase this 6 times 6. Okay. I will need Nurul Aiman. Okay, Aiman, Nurul Aini, Nadira, Nurul Aisha, and Nurul Amalina. Okay, please get ready. Okay, Aiman, Aini, and Aisha, Amalina. Okay, 4 of you can help to answer. Okay, this. So we will go element by element. Okay, so let us start with this this one. Mana siap ni? This one. Okay, can you help? What is the value for this?
One, two, eight, four,
Okay, 128.46. So next value For this one, so you are going to follow. For those who still do not know what you need to do, you have determined the AE, 12 EI, and so on here. Okay, in your earlier, your solutions. So we are just going to put this information according to this template. So next, anyone?
9, 5.
95385.6.
Here we are taken out. Can you take out the power 3? So it will be 95.39 about here, right?
Yes.
Okay, so next will be this one.
-1728. -1728.
Can you recheck?
Salah.
Or I have taken out wrongly. 4,824.
2880.
So in power 3, it will be 2.88.
Yes.
Yes. Okay, yeah. So be careful. This is lambda y. So next, this one. So this is basically same with this one, right? If you can see that only we applied negative, right? So we will continue to put in the 128.46 but in negative. Okay. Similarly, this one will be same with this one. Okay, same with this one. Oops, just too much, too messy. So we'll continue with negative 95.39. And yeah, this will be exactly the same, okay, with the K13. So it will be negative 2.88. So we solve for row number 1, okay. So that is why you need to know the steps. If not, this will be taking you a long time, okay. So then the next, okay, the next one will be this row. Can we continue with row number 2? Okay.
89.86.
Can you recheck?
Okay. 95.39.
95.39. Okay. If you can see that it's actually the same with this, right?
Yeah.
So next one is yeah, it's not same with others. Yeah, please. What is this value?
128.46.
Can you recheck? It's different. Just now lambda
Oh, terbalik. Okay. Yeah.
terbalik. This is lambda y right now. Wait.
Seventy-two point eight two.
72.82.
72.82. Okay, let's continue. This is also different. Okay.
3.84.
3.84. Okay. Then there will be continue, right? Continue with the same thing, repeated same thing with the negative. Negative 95.39 and negative 72.82, and this will be exactly the same. Okay, so 3.84. Okay, if you can see that. Okay, they are actually repeated but with different opposite sign. So next, third row.
This 2.88.
Yeah, it is the same with this, right? Yeah, row 1, K13. So negative 2.88. And this also same with K2, K23, this one, 3.84. I think from now we can just find the similar. Oh, this is not, this is totally new.
24.
24.
Yes, correct. So next, it will be repeated again, but in the opposite sign. Okay, so negative 3.84, and this is new.
12.
12, thank you. So how we can continue with this? Okay, so basically this row 3 is again for row 1 is quite similar but opposite sign. Okay, so then we can take down. Okay, negative 95.39, 2.88. Okay, and then 128.46, and then 95.369, and then 2.88. Okay, and row number 4 is also exactly opposite. Okay, same value but opposite. Okay, so we just copy it down. Negative 95.39, negative 72.84, and negative 3.84, and 95.39, 72.82, and negative 3.84. Okay, so the last one also, yeah, the last one is, if you can see that exactly the same value and the sign, but somehow there are difference in some of the location. So be careful as well when you copy down. Okay, so if 2.88, okay, then this is 3.84, and we have 12. Okay, we have 2.88, and we have negative 3.84, and 24. Okay, are you able to determine this? It looks scary, but yeah, you can do it. Okay, maybe I give you 1 minute to complete this. Then I will talk about the numbering. Then we have a break of 5 minutes. Okay. Okay, class, I need to continue with this numbering. NX, NY, NZ, FX, FY, FZ, and I hope to get back your attention. Okay. So if you can see that we need to give a numbering for this 6 times 6 matrix. Okay, how to give the numbering? If you look at here, we have this NX, NY, NZ at the near end, and also FX, FY, FZ at the far end. So you need to refer to your numbering of the DOF. Okay, so for example, here we are looking at element number 1. Okay, so if you look at near end, we must name with the X first, NX, which is 4. Then NY, which is 5, and then NZ, which is 6. So we need to name 4, 5, 6. Then go to the far end, FX 1, FY 2, and FZ 3. So 4, 5, 6, 1, 2, 3. We need to give a naming like this. So you write it here, 4, 5, 6, 1, 2, 3. 4, 5, 6, 1, 2, 3. Okay. So we will continue after 5 minutes, okay, for K2. Okay. Okay, class, can we continue? Okay, this round we need to do it faster. Huh? Can we get other set of, yeah, maybe we call just now is who? Now we call Nabila, Nadiatu to help right now. Huh? Are you here, Nabila and Nadiatu?
Yes, doctor.
Okay,
Yes,
yeah, let's start. Okay, now I want to get your response on how to calculate this lambda x and lambda y, or in your appendix is cx and cy. Okay, so for element number 2 right now. So what is your opinion?
Do 12 minus 6 over 6 y equal to y.
Yes, yes, correct. And then how about lambda y?
44.5 minus 4.5 over 6 equal to 0.
Yes, yes, you are right. So we are just using the coordinate, okay, x and the y, okay, of the far end minus the near end and divide by the length. That's all. Okay, so I will come back to you with this AE. Let me fill in first. So just now you said it's 4.5 minus this. No, this is 12 minus 6, and this is 4.5 minus 0. 4.5, which is 0. Okay. So next, I would like to know the value of AE over L, 12 EI over L cubed, 6 EI over L squared, 4 EI over L, 2 EI over L. So basically everything are the same, okay, from K1 except the length only. So this is the beauty. If the EI is different, you just multiply 2 EI, 3 EI, and so on. Okay, so come. Can you give me a value for this AE over L?
250 times 10 power of 3.
Okay, correct. About 2?
2,500.
Thank you. How about 6 EI over L squared?
7,500.
Thank you. How about this?
30 times 10 power of 3.
Okay, correct. And?
15 times 10 power of 3.
Okay, so well done. So you have calculated this. And we are going to put this again in our this complex. I would say this is quite complex here. Okay, so maybe we are going to get helps from others. Okay, how about now? Siapa? Radia? Rabiatu? Are you here?
Yes, doctor.
Okay, so maybe two of you can help me to fill in this this template. Huh? So let me make it big. Okay, so now this is 10 power 3. 10 power 3. This is 10 power 3. Okay. So if you are ready, just give me the value. Okay. So for K11,
250.
correct? Yes.
0.
Can you recheck? 0. Yeah, you're right. So it is 0. Yes, you're right. This is 0.
zero.
Is 0.
Negative 250.
Yes.
0 and 0.
0 and 0.
0, 0.
Yes. So we can move to the second. So this one is more easier, right? Yeah, whenever with lambda x, lambda y, then we can put it 0. Okay, then
0.25.
again 7 point
0.25.
0. Can you recheck again?
Okay.
2.5.
You get 2.5. It's different from my.
4.5.
Yeah.
2.5.
Yes, you're right. It's 2.5. So next.
7.5.
Okay.
0.
0. We continue, right? With negative 2.5 and 7.5. Okay. So we move to row number 3 now. Lambda 0, correct? Then
7.5.
correct. Yeah, this is repeated, but this is new. So it will be
26.
I thought this is 30. 30, right? For EI over L.
Yes.
30.
Yes. Then we continue with 0. Now we repeat. Okay, so negative 7.5. And this is new. Okay, 2EI over L we can get directly from here. Okay, which is 15. Okay, then we, for these two rows, I suppose we just negative minus the above, right? It is repetitive from this two row. Okay, if you recheck again, yeah. So this is just opposite. Okay, so similarly for this. So I can directly copy it down with the negative version. What happened? Jump. Okay. Negative 250, 0, 0, 250, 0, 0, 0, negative 2.5, negative 7.5, 0, 2.5, 7.5. Then the last one, some has the same, some is different. Can you help me again? This should be 0, then
7.5.
7.5, then
50,
15,
15.
correct? 0,
0,
0.
7.5,
7.5,
Negative
30.
7.5. And 30.
30. Okay. How about the naming?
Negative.
Negative
Madam.
7.5. Yeah, you're right. Negative 7.5. How about the naming of this one? Maybe we need to go back to look at our elements numbering. Okay, can you provide the numbering? 1, 2, 3, then?
7, 8, 9.
7, 8, 9.
Yes. 1, 2, 3, 7, at 9. 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9. Okay, but I forgot to change this to K2. This is K2. Okay, so don't confuse this K2. Okay, we are going to gather this K1 and K2 to become a structure stiffness matrix right now. Okay, let me gather this. Okay. You no need to recopy, you just use your inputs into your so now in the problem, they don't request for the the complete structure stiffness matrix. So to save our time, we don't need to determine the whole thing. We need to determine the elements in the structure stiffness matrix that will help us to solve the unknown displacement. That's all. Okay, so therefore the concept is here. Maybe I create another. Okay, you need to be very clear that we are actually doing all this is for the stiffness equations. Now I remember we have one more vectors we haven't found. Okay, Q equal to K D plus Q naught. Okay, we have determined the Q, we have determined the D, we haven't determined the Q naught, but we have almost done with the K. Okay, all these are global stiffness equation. Okay, what we have done earlier is just to prepare for this equation. Okay, so if you can see that you have a vector of Q with a size of 9, right? 1 up to 9. Okay, and equal to this K, okay, will be a size of 9 times 9. And the D is a vector of 9 times 1. Okay, this is just an idea. Okay, of course, in your real solution, you no need you no need to provide this, and you have this Q naught. Okay, the Q naught, the size is also 9 times 1. Okay, so if you want to prepare this complete set, it might take you a very long time. Okay, in the manual calculation. So what you can do here is we just find out the K, especially for the K. Just find the elements that will support us. Okay, so we need the partition. Remember, we have already done for one partition. Okay, which is for D. D1, D2, D3 are unknowns, right? Then we put the partitions here. So we need another vertical partition. Okay, and you must know that this K value, the K matrix is a square matrix. Okay, so if you are partitioned at row number 3, you need to partition also at the column number 3 after number 3. So it will have a size of 3 times 3 matrix here. Okay, this region will be the elements that will be helping us to find our unknown displacement. Okay, so we need to prepare for this. Okay, later when you want to find for your support reaction, which is the unknown Q, you start with 4 until Q9. Then you are going to require for this. Okay, so you will need to request for, where is my pen? Oh, it's here. This one. The elements here. We will need it. So in our problem just now, this is the answer that requested, okay, for D1 to D3. Therefore, this region, let me give a name like K11 must be found. Okay, then also we need the answer from support reactions. So therefore, this K21 must be found also. So now we are going to find this K11 first. Okay, so you need to check. You need to make sure that these are all zero. If any chance that this has values, so your columns that were associated with that row, you need to find also. For example, if row 5 has value, so column number 5, you need to determine also that elements for this stiffness matrix, but not for this case. So now we are very clear right now. If the D has 3 unknowns, so we only need to find 3 times 3 stiffness matrix to solve the D. Okay, so here we are going to find the structure stiffness matrix. Okay, so what I want to find here is, let me use, okay, structural stiffness matrix. K is equal to K1 plus K2. And we don't find all, we find partly the region K11, okay, which is associated with 1, 2, 3, 1, 2, 3 only. So we have 10 power 3 here. Okay, let me ask helps, okay, from your class. Now can I have Shamimi and also Azhani to help? Are you here? Shamimi and
Yes,
Azhani?
madam.
Okay,
Yes, yes.
come. Okay. Do you know how to do that?
Yes, yes.
Okay, come. So how to get the K11 here? Get this. Oops. Yes,
345.39.
3, 4, 5. Mm, okay,
Doctor, I
yes.
think you circle the wrong part.
Wrong part, huh?
128.46.
Oh,
Thank you, thank you, thank you. So when maybe, okay, start again. This one. This one. Okay. So the answer is
378.46.
okay. Thank you. So let us continue with 2, 2. I think my 2, 2 is this one.
Beside the 1 doctor,
Ah,
the 95.39.
really? 2, 2. Oh,
Oh, two, yeah, that's
yeah,
right.
correct.
But
Yeah.
yeah.
because
Are
my
we finding for the 2, 2?
no 1 2
2, 1. Oh, yeah, 1, 2.
yeah 1 2 1 2 is where 1
I
1
think it's beside the 72.82.
now my 1 is not
The
the
95. The 95.39.
I'm finding this. I'm finding this.
Oh, 2, 1.
Ah.
That is 2, 1, right? So the above it.
Yeah,
Ada.
95 point.
Yeah.
All right. Okay. Okay. And another one is row 1 is 0. Okay. So we have a value of 95.39. So can we continue with this? Correct?
2.88.
Okay. So let's look at the row number 2 now. Row number 2, 1. Okay, so I don't want to circle anymore, please. Maybe I put a star here. 2, 1 is here.
95.39.
2, correct? Yeah, anyway, it is mirror. Okay, so 2, 2 now. Put a double star.
75.32.
Yes, correct. Continue.
3.66.
Thank you. Then
2.88.
yes, continue. 3.66, then
54.
54. Thank you very much. Okay, you have done for this. Okay, so but we forgot about this, Q naught. Okay, we need to prepare Q naught before we can solve for the D1 to D3. So for Q naught, which element do you need to determine the Q naught? Which element you
1,
need
2,
to,
3.
which element you need to determine the Q naught? Q naught is when your element has loading.
Element 2.
Yes, you're right.
2.
So we are going to find the Q naught for element number 2. Okay, so please go back to the appendix and find the appropriate equations. While I'm going to get ready with the patch. Okay, Q naught. Do I have any template for this Q naught? Let me change.
Okey. Saya nak tanyalah. Paling nervous sekali dengan mana? Apa yang mana yang saya buat berhad siapa?
Maybe I will just modify from here. So we have a 6 meter length, we have 50 kilonewton per meter. Okay, it's very difficult for me to change it now. I will just amend here. Okay, we have a 50 kilonewton per meter and we have a 6 meter here. Okay, so therefore this is not the answer. We are going to get the answer for here. Okay, too bad. Okay, we're going to redo this. Okay, so here we have a template WL squared over 12 for the moments. So for the moments here we have WL squared over 12. Okay, and this is the same thing but at the negative. Okay, WL over 12. So W is 50, the length is 6 squared over 12. Can you get me the value of this?
150.
150.
Okay, 150. Okay, kilonewton meter. So here you will get 150 kilonewton meter. Okay, why it is positive? Because here already drawn the opposite direction with this. If you feel like confused, you follow these equations and you get the negative value. Okay, so for the vertical reactions, we get WL over 2. So it will be WL over 2, which W is 50, length is 6, and we'll have divide by 2. Okay, can you know what? Can I get the value?
Also 150.
150.
50.
Okay, done with that. And we need to give a naming to this. Q naught. I couldn't remember your naming. So it will be associate with 2, 3, and 8, 9. Right? 2,
Yes.
yeah, 2, 3, and 8, 9. Okay, so we are going to name it. This is Q2 naught, Q3 naught. Forget. I forget.
Q9 not. Oh,
Q,
that one Q8.
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 This is Q8.
That
This
is
is
Q9.
Q9. Okay, thank you very much. So now you have done with this. So we can put this into the vector. Okay, if you want to write the vector here, there is no problem. We can write it here. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we can put in the value of 9, for example, negative. Number 8 is 150, positive. Number 3 is, and 2 has value of positive, and the rest are 0. Okay, so this will be your vector for Q naught. Okay, so once you have done this, we are going to gather your K, Q naught, Q, and D into the stiffness equations. Okay, let us do it. Okay, so we are going to get this done. Huh? Okay, so how? Let me get the Q, K, okay. Q naught, and the K, okay, so you have to gather all this and putting into the equations. Where is the Q? Q equal to K D plus Q naught. Okay, of course, please put your document in the better way. Okay, so but it will definitely it will seem something like that. Okay, Q equal to KD plus Q naught. Okay, then you can create these three simultaneous equation to solve your D1 to D3. Okay, yeah, please take some time. I give you oh, it's the end of the class. So maybe I will provide the answer later. Okay, so this is how you arrange your Q equal to KD plus Q naught. And then you need to determine this region, K21 region, okay, when you want to find for the Q4 to Q9. Okay, so I'm going to give you the answer. I shall give you the answer now, okay, for you to check later. Okay, so these are the answer. Okay, so can you write down the answer? Okay, so the answer for D is the answer for Q is okay. So I will also show you this how to determine the internal forces. Okay, from the stiffness equation. Okay, in my other video. Okay, but if you do not want to use the matrix to solve your internal forces, you can actually use back your knowledge in the cut section method. Just because you already saw for the support reaction, you can just apply the support reaction into the your real structure, and then you cut section, and then you can determine the axial force, shear force, and the bending equation. Okay, for the internal forces at all your your elements. Okay, so but there is a way using the stiffness equations to solve, okay, for the internal forces that I will cover in my pre-record, my next video. Okay, so that's all for today class. Okay, so I think we have taken many times in the delay of my writing. Okay, so I hope next tutorial will be better. Okay, I will see you for next next class on the tutorial to solve for a composite structure. Okay, so class, thank you.
Okay, doctor.
Thank
Thank
you,
you,
Thank you,
doctor.
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 Thank you.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.